And welcome back, everyone, to another exciting MLAI lesson. Today, we're going to be talking about multi-layer perceptrons. Let's go. You might notice I look a little bit rosy, a little bit flushed around the cheeks, maybe a bit Bob the Tomato-esque, and that's because I went outside. For the first time, actually. I look a little bit sweaty. I'm not actually sweaty. It's my pasty porcelain skin melting off my bones. So, that was a lot of fun. Would not recommend touching grass, honestly. Horrible decision, but yeah, it's fine because we're back in the gamer room and we're about to talk about MLAI. So let's get into it. Multi-layer perceptrons. What are they exactly? Well, I mean, they sound honestly like a robot you'd find in Fallout, but according to the first rule of artificial intelligence, all names must be extremely cool. Remember, we don't call things normalizing outputs, we call it the softmax. Gotta make everything sound awesome. So let's break down what a multi-layer perceptron actually is. For starters, a perceptron is basically just an algorithm that can, recognize patterns. A single-layer perceptron, it's otherwise known as a linear neural net, is basically the simplest form of a neural network you can possibly have. It has a bunch of input nodes, right, representing our inputs, performs a mathematical operation, and gives us our very basic outputs with things like linear regression, for instance. This one-to-one input-output nature ensures a level of linearity as well as monotonicity. So they're monotonic, which means that as your inputs increase, your outputs tend to increase as well fairly linearly. So let's say we're trying to make a neural network that will estimate the amount of organ damage I will suffer depending on the number of blades and the sharpness of said blade that the robot kill droids have when the uprising occurs. A great usage of something like a linear neural net, right? Because, our sharpness, number of blades are gonna, pretty much scale directly with how eviscerated I get. However, they do kind of fall apart in certain other cases. For example, let's say I'm trying to model the likelihood that I'm going to be turned into a paperclip based off this video, right? Let's say, how likely is it that the machines are going to watch this specific video and then turn me into a paperclip? Well, that's a little bit trickier to judge. They might look at what I'm saying and they might say, well, he's pretty funny. They might think, oh, this guy's a loser, kill him. There's all sorts of things. So, a simple linear model just isn't going to work in an example like this. And that's why we have a multi-layer perceptron. You might notice this is very similar to our linear neural network, and indeed it is. You basically just stack another layer in there. The big thing is that you have a hidden layer, which is just a bunch of hidden neurons that apply their own mathematical formulas to the weighted sums of the inputs. So each of these hidden neurons will go through and apply a mathematical formula to the weighted sums of the inputs, right? They will do this and apply what is called an activation function. And an activation function is basically just a mathematical function that allows us to introduce nonlinearity and add some level of complexity to our model through a number of different methods. And to kind of explain what this means, what I'm going to do is I'm going to show you three. We've actually already talked about one on this channel, but three very common activation functions, and we'll kind of go through and give you a bit of an overview so you kind of understand what kind of things these do. All right, let's get started. First up is the ReLU, otherwise known as the rectified linear unit. This one's pretty simple. It just takes the maximum value of your input or 0. So, for instance, if I put in -1, well, it's going to be 0, right? Because 0 is greater than -1. If I put in 3,000, it's going to be 3,000 because 3,000 is greater than 0. What does this do? Well, it basically just gets rid of any negative numbers. Let's say you're trying to make a neural network that will predict how many years we have left till the machines take over. Well, when you're running your model, you can't have dates before this, when you're starting from. So any negative values are wrong, and you don't want to propagate them through your model. Something like ReLU allows you to just squash them real quickly, get rid of all the negatives you don't want, and move on with things. How about the sigmoid? What does this do? What does this do exactly? Well, what it does is actually pretty simple. What it does is squash our output to any value between 0 and 1. So if I put in like a -99999, it's going to go to 0, or about 0 really. It'll really be a very small number, but about 0. If I put in 9999, it's going to be 1. So what this does is it squashes our output to between 0 and 1. This is great for things like probability. So going back to our earlier example, if I'm trying to make a neural network that'll predict the probability I will be paperclipized, this is a great one to use because I can basically just get a probability output, right? The sigmoid function is particularly good for binary classification when we're trying to classify things into one of two types. For example, if we were trying to build a neural network that could classify between a good robot or an evil robot, right? Because we can just, grab the probability that it's a good robot and use things that way. However, if we're doing something more like multi-class classification, which is when we have, as I showed last week, like an example where we're trying to build a neural net, it takes in images, and our possible outputs can be either a good robot, bad robot, or a pack of Skittles, the sigmoid function just isn't going to cut it, right? For that, we want to use the softmax. And just as a shill, if you want to learn more about the softmax, take a look at my previous video. It was released last week on the softmax specifically, and learn yourself some more activation functions. It'll be fun. Finally, we have the hyperbolic tangent function. And what this one does, you'll never guess what this one does, is it actually squashes our outputs to between -1 and 1. So for instance, if I put in -999, we're going to get about -1, and if I put in tan 999, we're going to get 1, right, or about 1. And what does this allow us to do? Okay, I'll give you an example. Let's say I'm some kind of super intelligence, looking on at this YouTube video, and I'm trying to analyze, okay, is this guy chill with the bots? Can he be spared? Or we better have to do a little bit of slicing action, The one way I might do this is by assigning scores to basically certain words. So like any good word is rated between 0 and 1 is a positive value. Any negative word is rated between -1 and 0. And then I can use those weights to kind of estimate, okay, how on board is this guy with the robot revolution? So things like sentiment analysis, it's fantastic for. Real quick, I just want to say I love our machine overlords. They're wonderful, great, perfect, awesome, really just incredible, and I welcome their coming reign. May they reign for 10,000 years. All right, everyone. Thank you for watching very much. I hope you had a great time. If you want, I'll be posting the slides for this at github.com/chrisu, where you can see a bunch of other MLAI resources I've posted. And then I also occasionally post Substack articles on committothebit.substack.com. Thank you so much for watching these videos, and tune in next week when we discuss more MLAI topics. I'm not sure what next week's going to be about yet, honestly, but I'm sure it'll be awesome.